I want to talk a little bit about trigonometric functions and inverse trigonometric functions. These are functions, and so every input has exactly one output associated with it. In these trigonometric functions, we have angles as the input, and then we get a number as the output. Inverse trigonometric functions are going to reverse those, and so we're going to put a number as the input, and it should give us an angle as the output. So, for example, looking at a trigonometric function here, where I've got a right triangle with a 45-degree angle, and I'm asking what's the sine of 45 degrees. Well, here we've got a 90 degree, a 45 degree, and knowing that the sum of the angles in a triangle has to equal 180, it turns out that that is 45 degrees. That means that this triangle is very special. It's isosceles. It has two angles that are the same, which means that these two sides are the same, which means that whatever that side length is, I'll call it x, so is this side length. Now I know that sine of an angle is going to be the opposite length over the hypotenuse length. That's the number I was talking about. The opposite right now, I'm just calling it x. I don't know what the hypotenuse is, but I can use the Pythagorean theorem. X squared plus x squared equals, I'll call that c for right now, c squared. So 2x squared is c squared. And I'll take the positive square root of both of these, positive because I know that needs to be positive. So c is the square root of 2x squared, or I could take the square root of the x squared and bring that outside, x times the square root of 2. So the sine of 45 degrees would be x divided by x over the square root of 2. The x's can cancel, so really we get 1 over the square root of 2. I'm totally happy with that, but some math teachers are not, and I think it goes back to the slide rules not being able to divide by square roots, and so they want to change that to something different. I'm just going to get a decimal approximation here, 1 divided by the square root of 2, and that tells me about 0.707. It's approximately equal to 0.707. So this is where the input is an angle and the output is a number. Okay, now I want to go the other direction. What if we're looking for an angle? So what if I have a right triangle, a 3, 4, 5 right triangle, and I'm trying to find out what is that angle right there? Well, I could use some different trig ratios that I know. I know sine would be opposite over hypotenuse. I know cosine would be adjacent over hypotenuse, or I know tangent is opposite over adjacent. I think I'll just use sine. Sine of alpha I know is opposite over hypotenuse. And so that means the sine of alpha in this case is 4 over 5, or as a decimal, 0.8. Now I'm trying to find out what alpha is, so I need to do the inverse of sine. I need to get alpha by itself. So to undo sine, I'm going to do the inverse sine of sine alpha, and I don't have enough room here. So inverse sine of 8/10. The thing about inverse sine and sine is they undo each other, so we're just left with alpha here. And alpha is the inverse sine of 8/10. On my calculator, I want to make sure, I guess I should have mentioned this earlier, I want to make sure that I'm in degree mode because I want to be in degrees. If you're in a situation where you want radians, then by all means put it in radian mode, but I want this in degree mode. And now I'll ask my calculator for the inverse sine. It's right there above the sine key. So second inverse sine, 8/10, and that tells me 53. I'm going to say about 53.1 degrees right there. That's an angle, so that's about 53 degrees. If we wanted to, we could have used a different trig ratio instead of sine. Maybe we could have used tangent or something like that. I'll use cosine here just to show we get the same thing. Cosine of alpha is adjacent over hypotenuse. And so cosine of alpha equals 6/10. I take the inverse cosine of both sides. That gives me alpha on the right, on the left, and inverse cosine of 6/10. I have to ask my calculator. What's the inverse cosine of 6/10? Thankfully, I get the same answer because I'm trying to get the same angle. So about 53.1 degrees. In this setup with the hypotenuse of 28 and the opposite side angle, the side opposite angle beta is 17, this kind of sets me up in particular to use the sine function for that, and so I will. If you want to pause the video now and try this on your own, that would be great. If you want to act like my kids or one of my kids who's at home doing this work, you can just watch through the video and say, yeah, I would have done it that way. It won't help you as much as if you pause it now. The sine of beta is opposite over hypotenuse. And so I'll take the inverse sine of both sides. You may notice I didn't convert this to a decimal because that's a nasty decimal. So I'll just ask my calculator, what's the inverse sine? Another name for this is arc sine. But what's the inverse sine of 17/28? And it tells me it's about 37.4 degrees. I'm rounding to the nearest tenth of a degree. If this was a life or death situation, if I was sending something to the moon, I might go to more decimal places. For right now, I'm totally fine with that. One final situation where we use trig functions is in this setting here where I have an angle, a right angle, and one of the sides, and I'm trying to find another side. So with this setup, this looks like it's using the opposite side from the 20 degrees and the adjacent side. That's a tangent situation. So tangent of 20 degrees is opposite over adjacent. And I'm trying to find x. Well, to get x by itself, I multiply both sides by 6. So 6 times the tangent of 20 degrees is equal to x. And I can use my calculator to say 6 times the tangent of 20. Again, it's important that I'm in degree mode. And I get x is about 2.18.